Aristotle and the illusion of falling. Imagine for a moment a world where the simple act of dropping a stone held profound philosophical implications. A world where the way objects moved revealed fundamental truths about the very nature of reality. This was the intellectual landscape of ancient Greece, a world dominated by the towering figure of Aristotle, whose insights shaped not only philosophy, but also science for nearly 2 millennia. Among his myriad observations and theories was his understanding of why things fall, a concept seemingly straightforward yet deeply intertwined with his broader view of the cosmos, a view that, while ultimately incomplete, laid the foundation for centuries of scientific inquiry and a perspective we now know as fundamentally different from our modern understanding of gravity. Born in 384 BC, Stagira to Athens, the epicenter of philosophical thought, where he became Plato's student at the prestigious academy. For 20 years, he absorbed the teachings of his mentor, engaging in rigorous debates and developing his own distinctive philosophical voice. Unlike Plato, who emphasized abstract ideals in a realm of perfect forms, Aristotle's approach was grounded in observation and the study of the natural world. This empirical inclination led him to develop comprehensive theories about physics, cosmology, and the behavior of matter, including his explanations for why objects moved as they did. At the heart of Aristotle's understanding of falling objects was his concept of natural place. He believed that the universe was composed of 5 basic elements, each with its own inherent tendency to move towards its natural location. Earth and water being heavier had a natural place at the center of the cosmos, which Aristotle believed was occupied by a stationary earth. Air and fire being lighter had a natural tendency to rise away from the center. Beyond these 4 terrestrial elements, Aristotle posited a 5th element, the ether, which constituted the celestial spheres, the realm of the stars and planets considered perfect and unchanging. According to this framework, when an object composed primarily of earth, like a stone, was lifted and released, it would naturally strive to return to its natural place at the center of the universe. This inherent tendency to move towards its proper location was Aristotle's explanation for why things fell. It wasn't an external force pulling the object down, but rather an internal drive to reach its cosmic home. The speed at which an object fell, Aristotle reasoned, was directly proportional to its weight. A heavier object containing more of the element earth possessed a stronger natural inclination to return to the center, and thus would fall faster than a lighter object with less earthy composition. This idea that heavier objects fall faster than lighter ones seems intuitively correct based on everyday observation in a world where air resistance plays a significant role. A feather indeed falls more slowly than a stone. However, Aristotle's explanation lacked the crucial element of controlled experimentation. His conclusions were based on general observations and logical reasoning within his broader philosophical system rather than precise measurements and the isolation of variables. This reliance on observation without rigorous testing was a characteristic of ancient science. Furthermore, Aristotle's cosmology did not include the concept of gravity as a universal force acting between matter. His understanding of motion was tied to the element's desire to reach its natural place within a static and finite universe. There was no overarching force pulling everything towards a central point, regardless of its elemental composition. The celestial spheres, made of ether, moved in perfect circles driven by an unmoved mover, a prime cause that initiated motion without itself being moved. This was a fundamentally different picture of the cosmos than the one we have today. Gravity is a universal force governing the interactions of all matter. Aristotle also grappled with the concept of void or empty space. He argued against the existence of a vacuum, believing that motion required a medium through which to occur. If there were no air or water or any other substance, then an object would have no way to move from one point to another. This rejection of the vacuum further complicated any potential understanding of gravity as a force acting across empty space. For Aristotle, the universe was a plenum, a continuous expanse filled with matter in its various elemental forms. The ideas of Aristotle about falling objects and the cosmos held sway for over 1500 years, dominating scientific and philosophical thought throughout the Middle Ages. His works were translated and studied in universities across Europe and the Islamic world, becoming the authoritative source on matters of physics and cosmology. Challenges to his views were rare and often met with resistance, as his philosophy had become deeply integrated into the prevailing worldview. It wasn't until the scientific revolution of the 16th and 17th centuries that Aristotle's physics began to be systematically questioned and ultimately overturned. Figures like Galileo Galilei, through his famous experiments dropping Objects from the Leaning Tower of Pisa demonstrated that objects of different weights fall at the same rate in the absence of air resistance. This was a direct contradiction to Aristotle's assertion. Galileo's emphasis on experimentation and mathematical analysis marked a crucial shift in the scientific method. Later, Isaac Newton's law of universal gravitation provided a completely new framework for understanding why objects fall. Newton proposed that there is a force of attraction between any two objects with mass, and that this force is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. This elegant law explained not only why objects fall to Earth, but also the orbits of the planets and the motion of the tides, providing a unified understanding of gravitational phenomena throughout the cosmos. The transition from Aristotle's geocentric model with elements seeking their natural places to Newton's heliocentric model with a universal force of gravity was a profound paradigm shift in scientific thought. It highlighted the importance of empirical evidence, rigorous experimentation, mathematical formulation in understanding the natural world principles that define modern science. So while Aristotle's explanation of falling objects based on natural place and elemental composition may seem rudimentary from our modern perspective, it was a significant intellectual achievement for its time. It was a logical and coherent system based on the observations available to him. His ideas shaped centuries of thoughts, and importantly, provided the foundation against which later scientists could test, refine, and ultimately revolutionize our understanding of the fundamental forces that govern the universe. His illusion of falling was a stepping stone on the path to our current comprehension of gravity, a testament to the enduring power of human curiosity and the ongoing quest to unravel the mysteries of the cosmos. If you found this exploration of Aristotle's ideas about falling insightful, please like this video, subscribe to TheAncientPhilosophers for more deep dives into the history of thought, and share your comments below. What other ancient scientific or philosophical concepts pique your interest?